Okay. So thank you, everybody. It's a great pleasure to have Deng visiting us, so to speak, from Princeton. Gia is an assistant professor at Princeton University, which he rejoined after a little bit of time away after getting his PhD from Princeton, where he worked with Fei-Fei Li. I think he was one of Fei-Fei's first students, and now well known of ImageNet fame. So after Princeton, he went to Michigan, and before he went back to Princeton, and he has received a number of awards, notably, the Sloan, the Career Award, as well as the Best Paper Awards at ECCV, as well as the Mar Prize. And his work is at the cutting edge of computer vision and machine learning, and so he's here to tell us about dense 3D reconstruction in the wild. Okay, so I will mute this and I will give the floor to Gia. Thank you.
Thank you, Stefano. Hello, everybody. It's my great pleasure to be here, and I would be very excited to share with you some of our recent work on 3D reconstruction. One of my long-term research goals is to create a universal 3D perception system. A universal system should be able to perform dense reconstruction, that is, to reconstruct the depth and motion of every single pixel, including the static background and the dynamic foreground objects. A universal system should be able to reconstruct arbitrary scenes, including weird objects and shapes that have never been seen before. In particular, the system should not rely on any semantic knowledge. It should not assume any known categories of objects or scenes. The system should just be able to deal with completely novel geometry. Why no semantics? It is not because I don't care about semantics. Rather, the hypothesis is that geometry should be the foundation for semantics, not the other way around, because it seems that evolution spent most of its time developing the visual system for interacting with the 3D physical world, not for describing it in language. If this is true, this may suggest that geometry is at least as difficult as semantics. Note that a particular application may benefit from both geometry and semantics. In this case, it is still useful to improve geometry independently of semantics, because such improvement is more likely to carry over to the larger system, even when the larger system already benefits from semantics. Regardless, universal 3D perception would be very useful. It is essential for robotics and AR/VR. Today, I'd like to share some of our recent work towards such a 3D perception system. I'll first talk about reconstructing 3D from just a single image. Then I'll talk about 3D from multiple views. Let's start with single image 3D. Why should we care about single image 3D? This might not be obvious because for robotics or AR/VR, we can always have multiple cameras. The main reason for studying single image 3D is for understanding static images and monocular videos. If you care about semantic tasks like object recognition, I think 3D is the key to few shot recognition, because with 3D shape, you can easily be invariant to occlusion and viewpoint change without seeing training examples from different viewpoints and with occlusion. For example, you probably have not seen this object before, but you can easily detect it in this new image because you can match its shape even from a different viewpoint. In fact, even the best object detector today still has issues with occlusion and viewpoint change. With occlusion, this car can turn into a bed. With viewpoint change, the car can turn into a cell phone. This also applies to understanding relations. In this example, we see two identical figures. Their interaction is only apparent with 3D. In fact, it can be useful to describe the spatial relations of objects from a single image. And we have constructed a benchmark for spatial relation recognition with human annotations. And we find that the best recognition systems today do not perform well and are in fact no better than the simple baseline using just 2D boxes as input. This shows that the existing models have no 3D perception. But will 3D perception help? We constructed another benchmark using synthetic data and human annotations. And we found that 3D input can make a big difference in recognizing spatial relations. Another reason to study single image 3D is for applications in computational photography, such as synthetic depth of field or view synthesis. Last but not the least, I believe that single image 3D is important even when you have multiple views, because monocular 3D cues can help resolve ambiguities in stereo matching, especially with textureless or specular surfaces. Now, hopefully you are convinced that single image 3D is worth studying. How should we go about it? A basic task in single image 3D is depth estimation. We can train a deep network to do this if we can collect ground truth training data. To do that, we can use depth sensors, but the problem is that they are tedious to use, have limitations in range and resolution, and fail on specular or transparent objects. So they don't always work. As a result, we only have RGBD data on limited types of scenes, such as indoor rooms and driving scenes. If we train a network on such data, it would work fine on certain types of scene, but would fail on arbitrary images. For example, on this image, the network thinks the sky is closer than the building in the center, probably because it assumes a room scene. So one key challenge of single image 3D is to get training data for images in the wild. I will now describe some of the strategies we have been exploring. The first is crowdsourcing. The idea of crowdsourcing is to get depth, ground truth through the human visual system. The advantage of this approach is that we can use arbitrary images on the internet. But there is one problem. We cannot really ask a human what is the depth of a particular pixel in meters. We instead ask alternative questions. For example, we can ask about relative depth. Given 2 points, which one is closer? This drew inspiration from earlier work that crowdsourced relative reflectance. We constructed a dataset of 500,000 Flickr images called Depth in the Wild. We randomly sample a pair of points per image and have humans tell us which point is closer. Given the relative depth annotations, how do we train a depth system? Prior work showed that we can train a network to predict binary ordering between superpixels and then perform optimization to solve for a depth map consistent with the predicted binary ordering. We propose a simple approach where we train a network to directly predict the pixel-wise depth map with a ranking loss that encourages the predicted depth map to be consistent with the annotations or ordinal relations. Empirically, we see that these human annotations help us get better depth on arbitrary images. This is a qualitative example. We can take the idea of crowdsourcing beyond just relative depth. In this follow-up work, we asked humans to annotate surface normals of randomly selected points. We developed a UI where the annotator adjusts a gauge figure until the orientation looks correct. With these human annotated surface normals, we can train a network to predict a per pixel depth map such that the predicted depth is consistent with the human annotations of surface normals. We now have human annotations of relative depth and surface normals, but one issue is that the annotations are very sparse. They don't give us the dense geometry like a depth sensor can. Now, one question is, can we get per pixel depth from humans? It turns out that we can. In this CAPR 2020 work, we managed to create such a dataset called OASIS. It consists of crowdsourced dense 3D reconstructions of rendered internet images. Given an input image, we ask humans to annotate certain 3D properties, including normals and boundaries. Then we solve for per pixel depth through constraint optimization. This is the Annotation UI, which allows a user to draw annotations and see a live rendering of the reconstruction. Let me show you a demo. Here, the user decides where to add annotations. They first select the region to annotate. They're now drawing boundaries of depth discontinuities. Now they're drawing boundaries of normal discontinuities. Now they are placing surface normals. They can sparsely place surface normals, and the UI will automatically interpolate. And then they can fine-tune the surface normals. Once they are satisfied with the current notations, they can see a live reconstruction and iterate from here. We have collected annotations for 240,000 images. On average, each image takes about 300 seconds. This means a total of 20,000 hours of human time. In terms of total human time, this is already larger than the scale of ImageNet, which has many more images, but each image is much faster to annotate. Now, let me give you some more details about the specific types of annotations we have. The first type is occlusion boundary. Occlusion boundaries are where there is depth discontinuity. And since there is occlusion, there is also depth ordering. We ask humans to specify which side of the occlusion boundary is closer. We also have folds, which are normal discontinuities. We also have surface normals. The user annotates sparse normals until the interpolated dense normals are correct. We also ask if each surface segment is planar or curved. Finally, if there are multiple planar surfaces, we ask if any of those planes are parallel or orthogonal. Now, with all these types of human annotations, we reconstruct per pixel depth by solving a constrained optimization problem. A natural question is how good the human annotations are. We compared the human annotations against sensor ground truth from the Tanks and Temples dataset. We see that the error is fairly small compared to the mean and standard deviation of the sensor depth. Interestingly, we discovered that a main source of error is due to the ambiguity in estimating surface normals. For example, let's say this is a ground truth geometry from a depth sensor. It turns out that each human annotated surface normal can be a little bit off and off by the same global amount. This global rotation can cause large errors in terms of absolute depth, even though the shape looks qualitatively correct. If we account for this global rotation by applying the best possible global rotation correction to the depth, human depth, then the depth error is reduced substantially. Last but not the least, because we have rich annotations, we can evaluate not just depth estimation, but also other subtasks for single-image 3D, such as predicting surface normals, predicting occlusion boundaries and folds, and instance segmentation of planes. For many of these subtasks, it was the first time such data was available for training and evaluation. In addition to crowdsourcing, we have also been exploring using computer graphics to get training data for single-image 3D. Using synthetic data is not new in computer vision. It has many advantages, including easily available high-quality ground truth. However, a main drawback is that we don't have a way to automatically generate diverse realistic scenes representative of the real world. A high-quality photorealistic rendering usually involves a large amount of manual effort by human artists. Here we ask if we can reduce the human labor by learning to generate synthetic training data. Let's first take a look at a typical pipeline of using synthetic data. A generator generates synthetic data, which we then use to train a network, which is then evaluated on real images. Typically, a lot of manual effort is involved in designing the generator, including decisions regarding shapes, materials, and scene composition. Here, we'd like to automatically optimize these decisions. For example, in this CVPR 18 work, we show how to optimize the 3D shapes used to render synthetic images. we used a genetic algorithm to evolve very simple shapes to form complex shapes in order to maximize the generalization performance on real images. We show that on a single image 3D task, using such shapes evolved from very simple primitives can outperform using manually curated CAD models. One drawback of this approach is that we are essentially optimizing a black box function, which evaluates how good a configuration of design decisions is in terms of generalization performance on real images. This black box optimization can be computationally expensive. In this follow-up work at CVPR 2020, we try to address this efficiency issue by observing that some part of the function is differentiable and has analytical gradients. For the non-differentiable part, we can use numerical gradients and combine them with the analytical gradients to get the gradients for the entire function. We call this approach hybrid gradients. And we show that using such hybrid gradients can improve the efficiency of the optimization and result in faster convergence. And we're excited to see more recent progress along this line, such as this AutoFlow paper from Google, which learns to generate a synthetic training set for optical flow. Now, let me describe yet another strategy for getting training data for single image 3D. The idea is to use web videos. In particular, we can run existing structure for motion systems on web videos. Such a system detects sparse feature points, matches them, and then solves for camera poses and depth. In the end, we get depth for a sparse set of pixels for each video frame. Such depth can be used as ground truth for single image 3D. However, one issue with this approach is that classical structure from motion systems are not very reliable. Many of these reconstructed depth values are incorrect. If we evaluate the depth ordering, the error rate can be as high as 28%. In this TVPR 19 work, we ask if we can improve the quality of ground truth depth by filtering out the incorrect reconstructions. Our idea is to train a quality assessment network that decides if each reconstruction is good enough. Our hypothesis is that this task is easier than 3D reconstruction itself. We just need to reliably identify a small proportion of good reconstructions because we had an unlimited supply of web videos. And it turns out that existing heuristics such as reprojection error do not work well for assessing quality. This plot shows that the reprojection error is poorly correlated with the actual reconstruction quality. This is because reprojection error only tells you how well the geometric constraints are satisfied, given the feature matches. But the feature matches can be incorrect to start with. So we trained a quality assessment network. Its input consists of manually designed features based on the geometry of the reconstruction and does not involve any pixel values. This way, the network can be trained entirely on synthetic data and generalize well to real images. And we do train our network using entirely synthetic data. Using this quality assessment network, we constructed the YouTube 3D dataset, which resulted in several billions of relative depth pairs that can be used to train single image 3D. And with YouTube 3D, we show that we can improve the state-of-the-art of single image depth in the wild. Now, having presented our work on single image 3D, I'd like to switch gear to Multiview 3D. Multiview 3D is a success story in computer vision. In general, we understand multiview geometry very well, and sparse reconstruction of static scenes can work pretty well. However, Multiview 3D is far from solved, in the sense that we still can't produce accurate pixel-wise reconstruction for an arbitrary video. Typically, classical multiview 3D approaches formulate an optimization problem over continuous variables, such as 2D motion and depth. And then they optimize an objective function that measures the quality of a solution. The objective function typically involves terms that measure the satisfaction of geometric constraints, which are analytical equations that describe how 3D points move in space and how they are projected into 2D images. Once we have an objective, we use an optimizer to search for a solution. This is typically an algorithm that iteratively refines the solution. A main limitation of this optimization-based approach is that the objective function can be hard to specify. Geometric constraints alone are known to be insufficient, and it is difficult to come up with heuristics and priors that cover all the corner cases. Another limitation is that even if the optimization objective is well specified, the optimization problem itself can be hard to solve, in that it can be highly non-convex, and the optimizer can be easily stuck in the local minimum. In the last decade, deep learning has emerged as a powerful tool. It offers a strategy that's quite different from optimization-based approaches. During inference time, we do not need to formulate an optimization objective. The solution is instead produced by a network with learned weights. Deep learning has been particularly successful for semantic tasks, where it was traditionally difficult to handwrite an optimization objective. Deep learning has been applied to multiview problems too. The early works typically use a generic convolutional architecture to map inputs to outputs. However, unlike semantic tasks, the success of these early deep networks on these geometry problems was not as clear-cut. While these deep networks can achieve fast inference, they generally do not outperform the best classical optimization-based approaches. And they're often difficult to train and do not generalize well to new data sets they were not trained on. Here, I will present a different strategy that still uses deep learning, but borrows significantly from classical optimization-based approaches. The overall idea is to design deep architectures that behave like optimizers during inference time. The strategy involves two main ingredients: recurrent iterative updates and analytical layers encoding geometric constraints. In particular, I will talk about DROID-SLAM, a classical vision task that seeks to build a 3D map of the environment and track the camera trajectory. DROID-SLAM has traditionally been approached using our knowledge of geometry. In particular, we know that the 2D motion or optical flow of a pixel is the result of the 3D motion t of a 3D point x. That is, we can write down a closed form analytical function that relates the 2D flow f with the 3D point x and its 3D motion t. This gives us an algorithm consisting of two steps. In step one, we can estimate the 2D motion of pixels. For example, by matching pixels using hand-designed features. In step two, we can formulate an optimization problem that finds the 3D points and 3D motion to maximally satisfy the analytical equation. That is, we try to make the left side of the equation as close as possible to the right side. However, this classical approach does not work too well. It is not very robust and has frequent catastrophic failures. Recently, there have also been approaches based on deep learning. In these approaches, a deep network is trained to directly predict the camera pose and depth. The deep learning approaches are sometimes more robust, but by and large, they have not been able to match the accuracy of classical approaches. In addition, they do not generalize well to new data sets. For example, this plot shows error from a standard benchmark. The three recent deep learning approaches perform poorly against DROID-SLAM, which is a leading classical approach. Here, I will describe a new system called DROID-SLAM, developed by us. It is much more accurate and robust than prior systems, classical or learning-based. It generalizes very well, and we train it only on synthetic monocular data, and it works well on real data, zero shot. DROID-SLAM is a deep network whose design is inspired by classical approaches and makes heavy use of the symbolic geometric knowledge we have. Now, I will show you how we come up with this design. Like in classical approaches, we first consider the problem of estimating 2D motion. This task is also called optical flow, if we estimate 2D motion for every single pixel. Optical flow has been traditionally approached as an optimization problem, unsurprisingly. Here we try to find a flow field that maximizes the visual similarity between corresponding pixels, as well as a regularization term that encourages plausible flow fields. The first deep network for optical flow was FlowNet. It applies a UNet to concatenated frames and directly predicts the flow field. It is very simple and very fast, but it did not outperform the best optimization-based approaches. Since FlowNet, deep networks developed for optical flow have been generally trying to incorporate more inductive biases used by classical approaches. For example, PWCNet was a very successful design that includes a warping layer, cost volumes, as well as limited iterative refinement on the image pyramid. Taking inspirations from the classical optimization-based approaches, we proposed a new deep architecture called Raft. The most important difference of Raft from prior work is that it behaves a lot more like a traditional optimizer. It starts with initial flow field and performs many rounds of iterative refinement. Raft works very well. It achieved large accuracy improvements over prior state-of-the-art. It's also very fast in both training and inference. And in particular, it generalizes very well to new data sets. Now let's walk through the components in detail. Given two input images, Raft first extracts features for each pixel and then computes visual similarities for all pairs of pixels. That is, for each pixel in the first image, we compute its visual similarity against all pixels in the second image using a dot product. This gives us a 2D similarity heat map for each pixel in the first image. Then we pool this similarity map multiple times to low resolutions to generate a pyramid of maps. These similarities allow us to construct feature vectors useful for refining the flow field. Let's say we have a current flow estimate for this green pixel. That is, the current corresponding pixel is the red pixel. Then we retrieve the similarity values from a small neighborhood around the red pixel at each level of the pyramid. For example, here we have 4 levels in the pyramid, and from each level we retrieve 9 by 9 values. We then concatenate all the similarity values to form a single feature vector for this green pixel. This feature vector essentially contains similarity information around the current flow estimate. It can tell us how good the current flow is and where are better similarities. Because of the use of the pyramid, we can include similarities from a very large area. Given the features retrieved from the all pairs visual similarities, we can refine the flow field using a standard convolutional GRU. At each iteration, the GRU outputs a new hidden state and an increment to the flow field. It's worth noting that although we are motivated by the fact that the GRU can be trained to behave like an optimizer, we have not specified any explicit optimization objective, and there is no explicit computation of gradients during inference. To train Raft, at each iteration, we compare the predicted flow to the ground truth flow. The final loss is the weighted average of the loss at each iteration, with exponentially increasing weights for later iterations. This loss encourages the network to behave like an optimizer, in the sense that it produces a sequence of predictions that converge to the correct answer. On Singtel, a standard benchmark, Raft improves prior result by 30% on both versions of the dataset. Raft is used by all of the top 3 teams in the Robust Vision Challenge, which emphasizes robustness and evaluates methods on a diverse set of datasets. Our approach can be easily adapted to depth prediction from stereo matching, which is essentially optical flow in 1D. We ranked first on the Middlebury benchmark at the time of publication. Our method is especially good at recovering fine details. These are quantitative results. We can also look at some visualizations. We can see that the fine structures are recovered well. We now have an end-to-end network that predicts 2D motion. What should we do next to recover 3D? A straightforward method is to just copy the classical approach, where we solve for 3D through optimization. In particular, we can formulate an optimization problem called dense bundle adjustment. We are given a co-visibility graph, where the nodes represent frames and edges connect co-visible frames, which are frames that share pixels. And we predict optical flow between each pair of co-visible frames. And we want to solve for the depth maps for all frames and the absolute global poses of all cameras, such that for all pairs of frames, the predicted flow is as close as possible to the flow induced by the depth maps and camera poses. Note that the induced flow is a closed form analytical function of depth and camera poses. This gives us a nonlinear least squares optimization problem, which can be solved by iterative algorithms like Gauss-Newton. We now have a basic approach to visual SLAM. We can run Raft to obtain optical flow for all pairs of co-visible frames, and then solve dense bundle adjustment using an iterative algorithm such as Gauss-Newton. However, this naive approach turns out to work very poorly. One reason is that the predicted optical flow has a lot of outliers, which will derail the bundle adjustment. Outliers can occur due to occluded or outer frame pixels, or due to dynamic objects and flow estimation errors. How do we exclude outliers? One idea is to predict an additional confidence map for the pixels to give outliers low confidence. But how does the network know which pixels are outliers? Another idea is to use feedback from the DBA optimization. The outliers are those pixels with large optimization errors. Now, putting these ideas together, the logical next step is to tightly couple the Raft iterations and the Gauss-Newton iterations. That is, we tightly couple a neural network and an optimization layer. The neural network shapes the optimization, and the optimization gives feedback to the neural network. Now let's look at more details. For each pair of frames in a co-visibility graph, we extract features and compute visual similarities. This is similar to Raft, except that we operate not just on a single pair of frames, but on all pairs of frames simultaneously. Then we perform iterative updates. And each update is on all depth maps and all camera poses simultaneously. Now let's look inside this update operator. I can now walk you through it. At each iteration, we take the current estimate of depth maps and poses, and we compute the induced optical flow for each pair of frames. Here we do it for frame I and j. What's important is that the induced flow is a differentiable closed form function of depths and poses. The particular expressions do not matter as much. And we'd like to emphasize again that this is done simultaneously for all pairs of frames in the co-visibility graph. Now, this induced flow is given to a convolutional GRU. The same induced flow is also used to retrieve visual similarities in neighborhood. And the visual similarities are given to the convolutional GRU. Given these similarities, the GRU can evaluate how good the induced flow is and suggest possible improvement. The GRU may also detect outliers by looking for very bad similarities. Now let's take a look at the GRU. At each iteration, the GRU outputs a flow revision and a confidence map. The flow revision is the changes to the flow field recommended by the GRU. The GRU also outputs a confidence map to give low confidence to outlier pixels. The last piece of the update operator is a dense bundle adjustment layer. Its goal is to answer this question: how should we update depth and poses such that the induced flow becomes better? Its input consists of all flow revisions, all confidence maps, and the induced flow. Its outputs consists of an update to depth and camera poses. The DBA layer operates globally on the entire covisibility graph. Its inputs are from all pairs of frames, and its outputs are for all depth maps and camera poses. Inside this DBA layer, we solve an optimization problem where the variables are an update to all depth and poses. The optimization objective is defined over all pairs of frames in the covisibility graph. For each pair of frames, we compute the flow induced by the current estimate of depths and poses. Then we revise the induced flow using the flow revision recommended by the GRU. We also compute a new induced flow after we apply the updates to depths and pose. That is, what would the flow be if we update the estimate of depths and camera poses? And we compute the difference between the new induced flow and the revised flow. Basically, in this optimization, we ask, how can we update the current depths and poses such that the induced flow can be revised as recommended by the GRU? Finally, to exclude outlier pixels, we use the per pixel confidence weights given by the GRU. Effectively, this optimization is only done on the subset of pixels considered to be inliers. One remaining issue is that this optimization is a nonlinear least squares and does not have a closed form solution. To address this, we linearize the objective using Taylor expansion, which makes it a linear least squares problem. Now, we have a differentiable closed form solution. This is also called a Gauss-Newton step. It is worth noting that we implement this layer as fully differentiable. That is, we backprop gradients through all of its inputs, including the revision flow and the confidence map. During training, we have a pose loss and a flow loss. At each iteration, we compare the current pose estimate with the ground truth. Also, we compare the induced flow with the ground truth induced flow. Note that there is no direct supervision on the confidence map, but because the DBA layer is fully differentiable, the network gets gradients for the confidence map and can learn to predict useful weights. This is a visualization of an actual confidence map predicted by the network. We can see that the confidence map makes sense in that the confidence on horizontal motion is high for vertical structures. Our full system is composed of a front end and a back end. The front end performs feature extraction and bundle adjustment over a local time window. The back end performs global bundle adjustment over a large global time window up to thousands of frames. We build a covisibility graph through simple thresholding of flow magnitude between frames. With custom GPU kernels, we're able to run real time with 2 GPUs. And our system is trained only on monocular input. To extend our system to stereo input, we simply augment the frame graph with the additional stereo frames. And in the DBA optimization, we treat the relative poses between the left and right frames as known and fixed. To work with RGBD video, we still treat depth as a variable to estimate, but we use sensor depth as a prior in the DBA layer. In this optimization, we have an additional term that says the estimated depth should be close to the sensor depth. This treatment is to account for the noise and missing observations in sensor depth. It is worth noting that there is no retraining needed for our system to work on stereo or RGBD. Now let's look at some results. Tartan is a synthetic benchmark and is also used by us as training data. The scenes are photorealistic, diverse, and challenging. Last year, in 2020, there was a SLAM challenge using this data. On the official test set, we have reduced error by about 60% in the monocular setting and the stereo setting. In addition, we are 16 times faster than the best prior system. URUC MAV is a standard benchmark with video from small drones. Classical approaches generally do very well on this dataset and do much better than learning-based approaches. And the best prior results are from classical methods. This plot shows the errors for each testing sequence, and the last column shows the average error. The dashed bars indicate catastrophic failures. Here we see that we have reduced error by a large amount. This is also on URUC, but with stereo input. We do much better than DROID-SLAM 3, a leading classical approach. This is on TOM RGBD, a very difficult SLAM benchmark. The plot shows the error for each testing sequence with the average in the last column. We see that DROID-SLAM 3 has frequent catastrophic failures. The learning-based approaches are more robust, and our approach has much lower error among all approaches. This is the results from ETH3D, another standard SLAM benchmark. The evaluation considers both error and catastrophic failure. The x-axis in this plot is the localization error, and y-axis is the number of testing sequences on which a SLAM system can get a lower error. The higher the curve, the better. We rank #1 on this benchmark and are much more robust than the second place. It's worth noting that our approach generalizes very well. All of our results across datasets and input modalities are achieved by a single model, trained only once and entirely on synthetic data. Let's look at some qualitative results. This is a sequence from ETH3D. These are results from two popular existing systems. Both of them failed midway through the sequence because of failure of feature tracking. This is our reconstruction. We not only successfully track the full trajectory, but also have much denser reconstruction. These are additional results from the Tangson Temples benchmark, as well as our own iPhone videos. We have also applied the same methodology to a number of other 3D tasks. For example, this is video to depth with a recurrent unit and a perspective endpoint analytical layer. It achieves 53% improvement over prior work. This is SyncFlow, estimating per pixel 3D motion from RGBD video of dynamic scenes. The architecture has an analytical layer that performs dense bundle adjustment with soft pixel grouping. It improved the state-of-the-art accuracy from 30% to 80%. This is a 6D multi-object pose estimation. The architecture has an analytical layer that does bidirectional perspective endpoints. We achieve the state-of-the-art on a standard BOP benchmark. I've showed how we can design optimization-inspired neural architectures to advance the state-of-the-art on multiple multiview tasks. Now, very briefly, I'd like to talk about the tool that addresses the common issue that you might encounter in training such architectures. This issue involves 3D transformation groups, which are matrix Lie groups extensively used in 3D vision and robotics. 3D transformation groups are used in some of the architectures I've presented. For example, when we want to average two SE3 transforms. Here we represent an SE3 transform as a 4x4 matrix. Because the SE3 group is not closed under matrix addition, we need to first map them into exponential coordinates, perform addition, and then map the result back. However, if you try to backprop through this computation graph in current deep learning libraries like PyTorch, you will likely encounter numerical issues. For example, if the input of the graph is the identity transform, PyTorch 3D would return a NaN gradient. To better illustrate the problem, let's consider this simpler graph with the rotation group. In this graph, a rotation is represented as a 3x3 matrix. And we have a matrix log operation that maps the matrix to a 3-dimensional vector psi. During backprop, we first get the gradient for psi. To backprop through this log operator, we multiply the gradient with the Jacobian of the log, which is a 3x9 matrix. And then we obtain a 9-dimensional gradient for the rotation matrix R. We call this gradient the ambient space gradient because the rotation matrix R is restricted to a manifold inside the ambient space of all possible 3x3 matrices. This ambient space gradient just tells us the best ascent direction in the ambient space without considering the manifold. That is, you can go off the manifold if you follow this gradient. There's nothing theoretically wrong with this ambient space gradient for backpropagation purposes because it is only used as an intermediate result. But computing this ambient space gradient can cause numerical issues because the formula can have many singularities. For example, this is the formula for the matrix log of rotation. It involves the inverse of cosine, which has a singular gradient at 1, which will be triggered by an identity rotation. To get around this numerical issue, one solution we found effective is to compute gradient in the tangent space instead. The tangent space at a point is formed by all the feasible directions along which you're allowed to travel on the manifold. The tangent space gradient is the projection of the ambient space gradient onto the tangent space, throwing away the orthogonal component, which is not used anyways. Practically, this means that we do backpropagation in tangent space. For 3D rotation, the gradient we get will be 3 numbers instead of 9. The 3 numbers represent coordinates in the local frame of the tangent space. Accordingly, the Jacobian of the log operator will be 3x3 instead of 3x9. It turns out that after you work out the math, tangent space backprop has several advantages. It's much simpler and easier to implement, and it's numerically stable. It is representation agnostic, meaning that you can use your preferred representation and the gradient is the same. And the gradient can be directly used to optimize over 3D transformation groups. And we have developed a plug-and-play PyTorch library called LeeTorch. It allows you to incorporate 3D transformation groups into your architecture as painless as regular tensors. That's all I have today. And of course, none of these works would have been possible without my former and current PhD students. Thank you. And I'm now happy to take questions.
Thank you, Jan. I would ask people who want to ask questions to use the raise hand so we can, assuming we have it. I have a lot of questions, but I leave it to the end so that those who have more urgent and maybe quicker questions can ask them first. I actually don't know if we can raise. So Edna, do you know if people are allowed?
I see hands raised. Can I just click to
yes, go for it. I don't see them.
Oh, okay.
Oh, there, no, now I see. Okay.
Oh.
Is that you?
I unmuted.
Hold on, Stephanie's here, so she will just speak up and you can hear her.
Hi, I had a question. I might have missed it, but how did you get in the monocular SLAM cases? How did you resolve scale?
Oh, in the monocular cases, you would always have scale ambiguity. So the evaluation takes into consideration the scale ambiguity. Yeah. So you would have to align the scale against ground truth.
And calibration, like in the YouTube videos or in the cell phone?
I'm sorry?
And what about intrinsics?
Oh, so in our system, we do right now. We are in our current benchmarking. We assume that the intrinsics are given. However, our system can be easily modified to support auto calibration. You just make the intrinsics as part of the dense bundle adjustment optimization.
Okay, I have one more question, and I might have missed it. How did you generate the synthetic training set for for your optical flow prediction?
Oh, optical flow, but that we're just using existing synthetic benchmarks. You know, flying chairs, flying things 3D, Sintal. I mean, those are just standard data sets people use, and we follow the standard training sequence, the protocol.
Got it. Thank you.
Okay. Any other questions? I see there's a
Xiao Han.
Go for it, Xiaohan.
Yeah.
Xiaohan,
I've
you
just unmuted Xiaohan.
Mute. Okay, can you hear me now?
Yes.
Yep.
Yeah. So yeah, all these are very awesome work, and the experimental results are on the the visual odometry benchmarks are amazing. I was very curious. What are the failure cases? When would the system fail? Right. Apparently, it works quite well on all these benchmarks. I'm just curious when it fails, or does it fail at all?
Right. I mean, it does still fail. I mean, one failure case we observe is sort of the case of extreme outliers. For example, you put a foreground object that almost covers the entire scene, right? All the pixels, and then the system can be confused. What is the foreground? What is the background? What is dynamic object? What is background? So in that case, it can still fail. So that's actually one of the failure sequence on ETH3D. So we think that this can be further improved by improving the training data we're using. Right now, the training data we're using contains some dynamic objects, but not a lot, not these extreme cases.
I see. Another question I have is in SLAM, typically we assume we have a video, right, which basically models which has the continuous motion. Now in the structural motion setting, we have unstructured images, right? So in that setting, the viewpoint change of each images will be much larger. I was wondering, will it be easy to modify the system to support that scenario, meaning we have a large baseline instead of very short baseline as in the video setting?
That's a good question. Right now, our system is certainly optimized for the SLAM case where you have continuous video input. It is not optimized for the structure for motion on ordered image collections. So I suspect it will not work as well. It's just because so the sort of with continuous video, sort of the small baseline, and sort of it will be easier for the dense bundle adjustment optimization to work. But we have not actually tested this on ordered image collections.
I see. Yeah, because I was wondering what actually contributes most to the performance improvement in the system, because we have at least 2 learning modules, right? One is the RAFT, as a learning-based object flow. The other is the DBA layer. I was wondering if because in the structural motion setting, if we can have a very reliable correspondence, let's say network, then the DBA layer should be easily attached to that, right? And then maybe in the structural motion setting, we can also apply the same pipeline.
Right. I think certainly there is potential to use the same ideas for structure for motion. We just have not sort of tested and optimized the system for that.
Yeah. Cool. Thank you.
Sure.
Okay. Any other questions before I go? I don't see raised hands. So usually we finish right at about this time. So maybe what we can do is we can thank Jia and stop the recording. And then I have a very large number of questions for you, Jia. So if you don't mind staying on, and anybody